So it's my pleasure to present Amir Gholami. He's a research scientist in Bear and the Skylab at UC Berkeley. He received his PhD from UT Austin working on large-scale machine learning, a research topic which received UT Austin's Best Doctoral Dissertation Award in 2018. He is a Melosh Medal finalist, the recipient of Amazon ML Research Award in 2020, Best Student Paper Award in Supercompute 2017, Gold Medal in the ACM Student Research Competition, and Best Student Paper finalist in SC14, Supercompute 14. He was also part of the NVIDIA team that, for the first time, made low-precision neural network training possible in FP16, enabling more than 10x increase in compute power through tensor cores. Amir's current research focus is on large-scale ML and AI systems. So I'm really happy that Amir is here. I've been following his work for a while, but only met him this year, actually, earlier this year at ICML. So it was great to meet you then, and really happy to have you present here. So take it away.
Thank you so much, Mohammed. Thank you for the nice intro, and thank you everyone for coming to the talk. Feel free to interrupt in the middle. This is supposed to be interactive, and would love to discuss any questions that may come up. So I wanted to today talk a little bit more about not the traditional work that I've been doing, which was more like lower level optimization with quantization and sparsity, but more taking a little bit of like a full stack view of where these agentic workflows are going. This is a joint work with many different people in our lab, including several undergrads and several PhD students. So one of the big revelations in LLMs was this function calling. Who here is not familiar with function calling in the class? Is everyone familiar with tool usage and function calling?
I think we can assume people know what that means. Yeah.
Okay, cool. So basically, this is actually was found by mistake. So if you ask like a math question from LLMs, if you ask this from earlier LLMs, the answer usually wasn't very accurate, right? So then people found that if you start giving some form of like chain of thought prompting and you provide some examples, the accuracy suddenly jumps up really high. And at the time, we didn't know why. At the time, this is kind of related to O1 model from OpenAI, which is if you increase the amount of basically work during inference, when you do chain of thought, you're effectively increasing the amount of work during inference, then actually the model will perform better. So we have this pre-training scaling, we have scaling, larger and larger models that seem to give us much better performance. But there's also this inference time scaling, which at the time when this chain of thought prompting came, people didn't associate this with inference time scaling, but it is a form of scaling the amount of compute that you have. Then we found that actually the performance increases significantly. And then, so people started building on top of this, but then there was still a problem, which was even if we do this inference time scaling, if you don't have a calculator tool, for example, at some point you're going to run into issues. And the reasons for this includes various things. One of them is that, if the LLM hasn't seen complex math, it won't be able to solve it. The other thing is related to tokenization, like large numbers are tokenized into multiple tokens. So there's some fundamental problems with that. The other thing is that, whatever you do, even with reasoning, if your LLM hasn't seen some data, then it won't be able to answer it, right? So all LLMs have a knowledge cutoff. So if you're deploying this in an enterprise situation that you have to get information from a particular database, you either have to go and fine-tune the model on that data set, or else you won't be able to answer the query. So people started to think about taking a systems level view and looking at this as if it's like a CPU. Your LLM is essentially like a CPU processor, and you have some memory, which is your prompt. You have some long-term memory, which we have this basically like a storage that you can do RAG type stuff and fetch things. But still, even with these things, you won't be able to solve the problem that I mentioned, which is knowledge cutoff and basically being bad at certain operations. So one of the ways that people started to resolve this was function calling. So basically the idea was, instead of letting the LLM memorize everything, what if what if I basically stop the execution of LLM when it wants to fetch some information? So we can invent some specific token that after that token is generated by the LLM, we would stop the execution and we would do something, right? And so the way that the notation would work is as if we are calling a function, right? So for example, if I ask a question like which company has a higher market cap, NVIDIA or Microsoft, the LLM can basically say, look, I need to go and look at NVIDIA's market cap today. So I need to, make this call, search parentheses NVIDIA market cap. This could be different arguments, right? And then there's a special token that follows this. At this point, I can stop the execution and I can go and actually run this, get the results, bring it back to the LLM and provide it as an observation. So that allows the LLM to use tools, right? So one of the ways to do this tool usage is what's known as React. Is everyone here familiar with React?
Yeah.
Okay, so basically it's like, thought, action, observation, right? So the action is the function call, you call the function behind the scenes, or you even call like another LLM and you provide the observation. But there is one big problem with React, which is it doesn't scale very well, right? So if you see, all of these. So when I ask a question like which company has a bigger market cap, NVIDIA or Microsoft, I can perform these two function calls, searching for NVIDIA market cap and searching for Microsoft market cap in parallel, right? There's no reason for me to come here again. When I provide the result for this, the LLM has to look at the query, has to look at the intermediate results, then say, okay, now I need to call another search query to get the Microsoft market cap. We provided that result. Then again, it looks at all of the prompts so far. And then it says, okay, now that I have both results, Microsoft has a higher market cap, right? This is a little bit of outdated data, by the way. Now I think it's the other way. So this maybe for two function calls, maybe this is fine. But when you have like 4, 5, 10, 100 function calls, this is not going to scale. Other than speed, another very big problem is that the LLM can get confused with the intermediate results that you keep giving it, right? So for example, if you're fetching some data and there is some observation that includes some data, which the LLM may perceive as, the answer to your original query, it may actually stop execution, or it may actually completely diverge and do something else, right? So this is not scalable. And if you think about applying these agentic workflows in enterprise, you always need like 99.999% accuracy. But with this kind of a framework, you can go beyond a couple of steps. And so some people tried this. So for example, there was a work on AutoGPT, which was trying to do this React type thing for, basically operating tools. And it doesn't scale, right? As soon as it takes 5, 6 steps, it completely diverges off from what the user was originally asking. So what can we do? So what we need to do is instead of trying to look at these LLMs as like a big black box and just try to come up with a better and better LLM and putting all of the tasks into this LLM and having it finally figure out what to do, we need to break down the task into smaller pieces. That's essentially how we develop code today, right? So if you look at non-agentic workflows, how do we write code? We write code using very small, well-defined functions, right? That have unit tests that are very, very like clean. And then we build an application on top of these, right? So you look at, for example, Google, any of the Google products, they're built on, millions of lines of code, but every, if you look at it, it's very modular, right? Every function is very clear what it needs to do. That's not how people are writing agentic workflows today, right? It's as if you have a basically like GPT, 4, GPT 3.5, and you basically throw all of the things in the prompt, you put a bunch of uncontext examples, and you kind of hope that it wouldn't get confused. But that doesn't scale. So let me show you an example. This is a real example, actually, from one of our sponsors, which the analyst, instead of asking whether market cap of this company is bigger than another company, asks a very broad question. So you may have a query that says, analyze the risk factors mentioned by semiconductor companies using their most recent 10K filings. Well, first you need to go and figure out what are the semiconductor companies that this person is asking. This person is located in the US, so these are the companies. Then you need to go fetch their latest 10K form, which is a pretty long context by itself. You need to run an agent to analyze the 10K form, and then finally aggregate all of these results and come back with an answer. Potentially, there could be like, some internal data that company has that you also need to call. So it's impossible to use a React type approach with this kind of a framework because with this kind of a query because the context length doesn't even allow it, right? But by looking at this, you can see the pattern, right? That if we had a way of telling the LLM, look, you need to break down the task to these pieces. You need to first go find out what are the companies. Then for each one of them, it's like a for loop now, right? So for each one of them, go do the analysis and then finally do a join operation, right? Then the accuracy will be higher and the speed will be higher. So another example, this is actually a work we did with Apple before they announced Apple AI, which was deploying a model completely locally on Mac, and they wanted to mimic Siri. So you can say something like, I want to have dinner with Lotfi and Sid Thursday night at 6 p.m. in Berkeley. I'd like to eat Korean food, right? So this is a very simple request, but actually it involves a lot of tasks for the LLM to perform. First of all, the LLM doesn't know who is Lotfi and Sid, right? You need to go and use the contact tool and try to figure out who is Lotfi and Sid. And then you need to figure out, okay, at 6 p.m., what is a good Korean restaurant that's open at 6 p.m. and it's, in Berkeley, right? You need to perform some search. And then finally, once you figure those out, you need to put like a calendar invitation, send a calendar invitation to Lutfi and Sid, right? So if we look at the steps required, this is what we want. We just basically say, hey, I want to have a dinner with these two people. This is the outcome. But to get to here, the LLM first needs to figure out Lutfi and Sid's email address. So basically, first thing that I need to do is to get the email address of these two people. There's some exception handling that may happen. Maybe I won't even be able to find their email address. I need to get back to the user. And then finally, I need to create a calendar invite. And to create a calendar invite, I need to have their email address and fill out the form, fill out the date, like April 24th at 2 p.m. So let's look at the execution graph. So imagine I magically gave you this, that this create a calendar invitation with Lutfi and Sid tomorrow at 2 p.m. translates into this intermediate representation. So first, these two tasks can be executed in parallel, getting email address of Lutfi and Sid. So I can basically use Apple's contacts tool to get that data. Let's say I get their email. Then I need to call this create calendar event using their email addresses, right? And this is, all filled out by the LLM, right? And then finally, I have the calendar invitation here. So now let's say we add that Korean restaurant part, right? Find a good Korean restaurant at Berkeley and send an email to Lutfi and Sid with the map link to the place, also create a calendar invitation for 6 p.m. tomorrow. As you can see, things can quickly become very complex, right? So we need to have a way of creating that plan systematically instead of basically giving everything to the LLM all at once and having it, figure out everything, which doesn't scale. And even if it can do that, it probably results in like a 400 billion parameter model that's not efficient. So let me get to the LLM compiler part. So basically, the LLM compiler idea is to break the tasks into a plan, much the same way that a compiler creates an intermediate representation when you're writing a code. So when I'm writing a Python code or like a C++ code, the first thing that happens is that the compiler takes my code and creates an intermediate representation, analyzes that intermediate representation, optimizes it, and then dispatches it to the CPU for execution. So let's say we go back to the earlier example. How much does Microsoft's market cap need to increase to exceed Apple's market cap? Let's say this is the query. So first, we have two options. Either completely give this like a React type approach to LLM and let that figure it out. But as you saw, there are examples where that thing doesn't scale. Or we can basically try to take more of a systems approach of first creating an intermediate representation of what the LLM needs to do. So first, the LLM needs to call a search function to get Microsoft's market cap. Then the second task is to search for Apple's market cap. And after you have these results, then you need to call like a math tool to compute the ratios so that you can figure out how much one needs to increase to exceed the other one. And then finally, you call another LLM to get back to the user. With this, then you can create a dependency graph. So with this, I can look at the dependency between these tasks that I have. So essentially, it's like, an intermediate representation that, you can see the dependency between different operations. So task 1 and task 2, if you see here, they don't depend on anything else. So they can be executed in parallel. Task 3 has a dependency on task 1 and 2. And task 4, which is the final LLM call, has a dependency on the third task. And then with this, I can basically start dispatching the calls to two different LLMs. Task 1 and 2 can be executed in parallel. They don't even need an LLM call. It's like an API call. And then task 3, which is a math operation, either it's a simple calculator or it's another agent that's like, expert in math. And then task 4 is another LLM call. So at this point, I can also decide to dispatch this to the relevant LLM with the right set of tools. Is this kind of framework clear? Go ahead.
Regarding the how the IR being created, like in the second LLM planner part, is that did by another LLM, or is there like a specific technique need to be applied? Since it looks like the key, as long as we can clearly like divide in our workload, then there will be more easier for the following up scheduling or execution. Like I'm interested about like how the granularity be decided and how it is being participated.
Was your question related to the second part or the?
For the LLM planner part, like how we are going to translate the user input into this kind of function call instruction.
Yeah, great question. So this is a dedicated LLM. So the job of this LLM is basically to create a Pythonic a plan, which includes the task dependencies. It basically has to follow a particular output. And there's some checks to make sure that this plan is accurate. If it's not, it goes back. So it's a dedicated LLM that does this. So you end up doing a little bit more work, but basically by creating this structure, it allows you to execute things faster later on, or actually more accurate later on. So to answer your question, this is a dedicated agent that goes and creates this intermediate representation.
Okay, got it.
Yeah, good question. And there's some details here of, what's, if you, for example, have like in the case of Apple, for example, there is a lot of tools that exist on Apple, right? You can operate many different tools, right? So this LLM planner itself, there's some details of, fetching the relevant in-context examples, fetching the relevant tools in its prompt, right? So that it can provide the right set of, plan basically, which is actually very interesting problem because this is actually a hard task to create this kind of a plan. But there is a lot of data that you probably have already of how the users are interacting with your agent that you can use to increase its robustness.
I see.
Great question.
The following up question is that does this LLM planner need to be fine-tuned, or like is there like currently existing language model like Llama 3 that can natively support this kind of planning using like a specific prompt? In the cases of the LLM compiler, like what do you guys do for creating this specific agent?
Yeah, so we have done both. So you don't necessarily need to do I skipped this a little bit, but you don't necessarily need to do a fine tuning. So if you look at like, basically the approaching this, first thing is select the right model, right? If Llama 3 is like, a good model for creating like Pythonic type plan, then that's a good one, right? But you can get a lot actually by prompting. So by prompting or by basically doing this kind of inference time scaling, that you increase the amount of reasoning steps that the LLM needs to do before it creates the plan. As we saw with O1 model from OpenAI, it gets you really far. But you can also do fine tuning. So we did the fine tuning part for the work we did with Apple, which was a 1 billion parameter model that is capable of function calling, right? That is capable of operating a Mac with Siri type input. And for that one, we needed a very small model that can have very high accuracy and that can run locally. So for that one, we did fine tuning. But what we've seen is that prompting gets you a long way, especially within context examples and including like chain of thought reasoning, doing a O1 type approach where you ask a lot of smaller models to come up with some reasoning, and then you have the model look at those reasoning and then come up with the plan. That gets you very far.
I see. Thank you.
I have a quick question.
Please.
I wonder, does the LLM planner it scales well? Because like in this example, the original prompt is just you compare the Microsoft market cap with like Apple's market cap. So it breaks into basically 3 steps: search the 2 brands information and the simple math, and you have a kind of. But what if I put like much more complicated questions, and then the number of instructions or the number of operations actually goes into much larger than 3 or 4. Does this planner scales well on this?
That's a great question. So it depends on how complex is the task. So the LLM planner itself is an LLM output, right? So it is prone to problems, right? So one of the things that we've put there is because we can have a verifier of looking whether the DAG is like a correct DAG or is the function call is the correct function call. We can basically, if it makes a mistake that doesn't pass that verifier, we can go back and refine it. So we have that, we have that component there. But you can definitely imagine a case where it involves, let's say, 1,000 steps that we're going to see these kind of AI agents, right? In the next couple of years, that they require like thousands of steps. They require communicating with other AI agents. This doesn't scale to like very, very large number of tasks. We're working on a second version of the paper, which tries to address that. But this is also prone to that problem. It works better than React, as I'm going to show you in a second, but it is prone to that as well.
Thank you.
Just to add to that, it's kind of similar to, I don't know if you've seen DSPy model, the DSPy framework from Stanford. This is kind of also similar to the DSPy, which is like tries to break things into more modular form that could be reasoned about, but still the part that breaks things into these modules is another LLM. So there is that weak link that needs to be addressed if you want to scale this to a very large number of steps. Great question. Any other questions here? Okay.
Can you talk about how you verify this? Because
oh yeah. Yeah, absolutely. So so one of the things is that, for example, these function calls are predefined, right? The LLM is not, coming up with like a random tool, right? So the tool, there's some consistency that you can do to make sure that the tools are not hallucinated. Second one is that this DAG needs to be a proper DAG, right? So it's a directed acyclic graph, right? So if it has some cycles, you can look at that and, you can basically figure out that those are like inconsistent. And then the other thing that's really important here is that every one of these functions, you can run unit tests around them. So for example, going back to the example we had here, like if for some reason this function comes back with not an email address, it comes back with some other not incorrect, for example, email, right? Or an incorrect output, we can provide unit tests around it to make sure that the output of this code is correct. And if it's not correct, then we can go back and perform error correction. Either another LLM or maybe a more powerful LLM is another way to verify the output. But if you have like a black box approach, then it's almost impossible to figure out what the LLM is doing and where is the problem. Did that answer your question?
Yeah.
Okay, cool. All right. So now the interesting thing is that, instead of treating this, if you take this system view, Andre Karpathy started, that first person to mention this was basically, if you think about like in hardware today, we have like efficiency cores, we have performance cores, right? Depending on the complexity of the task, we may dispatch something to the GPU, we may dispatch something to CPU, right? Here it's the same thing, right? Now that we have this breakdown, I can dispatch things maybe to a Llama 7B model, depending on the complexity. Maybe I incorporate like a Llama 7EB model and so forth, right? So this view allows us to even dispatch and utilize multiple LLMs. All right, so now let me show you some examples. So there's different types of tool usage patterns that you can imagine. that you know the user's request may result in. Like for example, the you know if you have a query like this, analyze Apple and Microsoft's latest 10K form and compare the sales forecast. Basically, these two analysis of Apple and Microsoft's market cap can be done in parallel, right? So this is usually called embarrassingly parallel, right? Because everything can be completely parallelized without dependency on each other. But you can have like, you know, cases where there is some kind of like a block or like a barrier in the middle that doesn't allow you to have like full embarrassingly parallel algorithm. But it's kind of similar to compiler like intermediate representations. So let me show you some examples with this pattern, which is most of the data sets right now follow this pattern, pattern A. So the table that you see here, there is two rows here, hotspot QA and movie recommendation. These are two different data sets that are popular and used commonly to test function calling, or you know, one of the data sets that's used for function calling. And you'll see different methods. React Dagger is our version of optimized React, where we provided a lot better prompts, a lot better in-context examples. OpenAI's parallel function capability. OpenAI supports calling multiple functions at the same time, and then LLM compiler. Then first we have the GPT-based results. This is with GPT, I think, of Turbo, and then with Llama 2 7EP. And we are measuring accuracy, total latency, and the speed up you get compared to React for both GPT and Llama 2. So first thing that you notice is that the accuracy of just using React is pretty low. So if you look at both the hotspot QA or movie recommendation data set, the accuracy is only 61%. The speed is also pretty slow. So it takes 7 seconds to perform these two comparisons, right? So this basically hotspot QA asks like, you know, a question similar to the one that I showed you, where you need to go and, you know, call two things, right? You know, first, you know, for example, look at Apple's market cap and okay, say what are the results, and then Microsoft market cap, something similar to that pattern. But then interestingly, you see that the accuracy will also increase significantly when you're using this kind of a LLM compiler approach, because React gets confused with intermediate results that come from the first function call. So you first make an observation. That observation may include some data, and the LLM may actually prematurely stop execution, right, and come up with the wrong answer. But when we're taking this modular approach, you have to basically complete all of those steps, get all of those observations, and then provide all of them at the same time to the LLM, which you know resolves that problem. And so you can see that both for movie recommendation and hotspot QA, our approach gets significantly better results than React, and with, of course, much better latency. But this is also true for Llama 2, right? You see 3% improvement, 7% improvement in movie recommendation with significantly faster speed. Also, interestingly, we get better results in terms of latency compared to OpenAI, because the way OpenAI performs parallel function calling includes a little bit of an overhead of, you know, they use like a JSON format, which is a little bit more expensive than the approach that we have, although their approach supports a couple of other use cases which we don't support. So there's a caveat there. All right. In terms of cost, so this is another important part. For React, you're performing all of these, you know, you're looking at all of these observations every single time. When I, for example, look at one observation, then again, I have to go look at the user query, all of the intermediate results I have had so far, and say, okay, now I need to call the second function call. Get that second function call, again, repeat everything and say, okay, now I need to go and call this third function. So the cost is very, very prohibitive. So here we're reporting the total input tokens and output tokens for different methods for hotspot QA and movie recommendation. So you see that React uses significantly larger number of tokens, 2,900 as compared to 1,300. This is expected because of this serial execution that React has. And the output tokens is also much higher compared to this LLM compiler approach. Any questions here? Okay. So this was more of like, you know, a static.
Go
ahead. Please.
Yeah, it should be okay.
Oh, it's good. So I was asking, what is the number of tokens actually different? Like, because it's still in parallel, but you're still giving the same prompts to everything and getting the same outputs, right? I imagine that the processing itself is slower because you're processing more tokens while you're doing the second prompt, because you're giving context the first prompt for it. But still the total number of tokens should still be the same, right?
No, it's not, but that's a great question. Thank you for asking that, because that's actually a very important point. So the way React works, let's follow exactly what happens. I provide this query to the LLM, right? Which company has a higher market cap, NVIDIA or Microsoft? It looks at this prompt and it says, okay, I need to go and fetch that data. So it starts generating these tokens. Thought one, I need to search NVIDIA's market cap. Okay, then it basically makes this function call, right? We make this function call and we provide this observation as of March 2024, etc., right? Then again, the LLM has to process now all of this data in its prompt. So query, thought one, action one, observation one. And it says, okay, now I have NVIDIA's market cap. What is missing? Well, I need to also search for Microsoft's market cap. Action two, call Microsoft market cap. We look at that, we provide the output, observation two. Again, now the React model goes back and looks at all of this again. And now it says, okay, now Microsoft has a high market cap. You see, it's basically, it's like, it's every single time you need to look at everything, right? And this prompt keeps growing and growing and growing. But when you break the problem into smaller pieces, if you look at this pattern that we had here, you don't do that, right? You basically just, you say, okay, what do I need to do? Well, I need to call this Microsoft market cap, and I need to basically perform this for Apple. That's it. You perform both of them. You basically call both of the functions, and you provide all of those at the same time.
Yeah, okay, so but for producing the final output, we will still have the same total number of tokens, but due to the intermediate processing, we saved some tokens from the result of the first query. We don't have to pass to the second one. Yeah,
Exactly. And you can see that, if you have more and more steps, the cost saving will be significantly more.
Yeah, they got the thing.
Yeah, that's a great question. And it's not only about speed. Accuracy, if you've seen React, if you run React, it prematurely stops because it looks at all those observations like, okay, I'm done, basically, which even though it's not done completely. Great question. So one of the interesting things here, which people are trying a lot because kind of like a very interesting agentic workflow, is taking multiple steps before you execute a task, like web navigation, right? So in web navigation, let's say, you're like, hey, I want to buy like, a particular item, right, from my house. What do? We first go to a website like Amazon, we try a bunch of different search queries, we look at the results, then we look at multiple return results, we compare reviews, we compare like price, we look at like aesthetics. Maybe I want a particular color that I need to check if that color is available and so forth. And then at the end, we basically make a purchase decision, right? So you can think of one of like, I don't know if you guys like follow, there's a lot of companies that are working on this. It's kind of like an RPA, robotic process automation, right? So I don't know if people here are familiar with that term, but it requires doing much more complex tasks other than just, the function calls that I showed you earlier. For this kind of a task, React doesn't work at all, actually, right? The accuracy is extremely low because HTML, if you look at like an Amazon page, the HTML representation itself is like 100,000 tokens for every page, right? And before you can perform this buy decision, you need to make sure that you've explored multiple items first before making the purchase, right? And how many items you need to explore depends on what's available, right? Maybe I search for a particular item and only 2 items are available, right? So after looking at those 2 items, I can make a purchase. But another task may require like 8, looking at 8 in parallel. So similar to the case before, we create a plan and we say, look, you need to first perform a search, which, there is some a function that can basically type something in the search and click on the search button, and then look at the results. In parallel, explore multiple different results, look whether they the return results satisfy the user query? If so, then return that. If it doesn't, then discard this, explore other items, and then at the end, choose the right item, go and purchase the right item, right? So this requires much more complicated set of steps. And actually, if you apply the LLM compiler type approach, you get the best accuracy. So right now, we have the best accuracy for this on with GPT-based model. So here we're reporting results with two different models, GPT 3.5 and GPT 4. React, the success rate is measured like out of 100 like purchase queries, did I actually purchase the right item? As you can see, React is pretty low, 20%. And its latency is pretty small because it usually, as soon as it sees the first item, it just basically purchases the item. Doesn't explore a lot, which is a big problem with React, which is premature stopping. LATS is another method that performs some form of like, analysis on the results and reflection and so forth. You can see the success rate increases, but the time is huge in terms of it spends a lot of time on exploring different things. But with the LLM compiler approach, the success rate is the best, and the speed is pretty fast. And I'm going to show you a demo of how that works. So this is a case where we're asking this agent to go and find a blue ON men running shoe for size 10, right? So men size 10. So what's happening is that the LLM created the plan, and it knows that it needs to now go and basically type ON running shoe for men size 10, and then it looks at the return results, and in parallel, it's going to explore multiple of them at the same time. Okay, so as you can see, it's opening multiple items in parallel. It's exploring multiple items in parallel. Then it goes and looks at every item and fetches looks whether the size 10 is available or not, and also looks at the review. It's looking at the size, make sure the size is available, closed all of the items, looked at the return results, and then it decided to choose one of them, the item that it chose, choose the final size, make the purchase. And with React, it stops after it looks at the first item. So just as a quick summary here, you have two components, right? You can, of course, fine-tune a model and teach the model how to operate these tools, and that's all good, right? If you have if you have enough data, you can do that. But for many agentic workflows, there's so many different trajectories, like a robotics problem. You can have so many different trajectories that probably it's very rare that you'll have data for every single trajectory. But the LLM compiler is kind of orthogonal to that. So you can either have a fine-tuned model or like a model like GPT and prompt it. It basically takes that model and breaks down the task into an intermediate representation that we can analyze, that we can basically make sure that the output of every single of those function calls is correct. And if it's not, we can perform an error correction, right? So it allows you to get better accuracy and faster runtime. All right. So then so when we publish this Apple, people, because we are mostly working on efficient model design at the edge, and lots of our papers are related to quantization and sparsity, Apple was interested in using the same kind of approach to shrink the model into a very small form factor that can be deployed on a MacBook, right? So we worked on this project called Tiny Agent, which uses a quantized model, 4-bit quantization, everything completely deployed locally, and it uses LLM compiler to get significantly better results. Actually, for the task that Apple cared about, this 1 billion parameter model exceeds GPT-4's function calling performance while completely running locally on device. So let me show you the demo first. What's happening here is we're setting Whisper to run locally. So this is Whisper v3 running locally, quantized also, and then this Tiny Agent 1B quantized with 4 bits running locally with Llama.cpp.
Create a meeting with Sid and Lutfi to discuss Tiny Agent tomorrow 12 p.m.
Okay, so what you're seeing here, everything is running locally. This is real time. It's creating that intermediate representation. So get email address of Sid is the first task. Second task is get email address of Lutfi, and then calling this function to create a calendar. So it creates the calendar event, gives it a title, gives it the start and end time, and the result from task number 1 and 2. So this intermediate representation is getting created with a 4-bit quantized model with just 1 Boolean parameter model running locally.
Create a reminder to follow up with Amir and Kurt next Friday 10:30. Send an email to Nick, attach the llmcompiler.pdf file, and ask when he's free to go over the draft. Send the directions to Berkeley Social Club to Ryan and Sehun with an SMS. Create a note about the summary of the llmcompiler.pdf file.
All right, so back to the slides. Okay, so in particular, this is a model that we trained by creating a lot of data, so synthetic data that we fine-tuned, like, what are the different types of, calendar invitations that you can create? What are the different ways that you can call like a map tool? What are different ways that you can write an email in this environment? And then we fine-tuned a model with LoRa, and we basically used like a Llama 1.1, 1 billion parameter model, and then afterwards, we quantized it with 4-bit precision, but we taught it how to create this planner, right? We taught it how to create that LLM compiler type plan and execute it that way. And it gave us significantly better accuracy. All right. So now what do we do if, in this case, we have like hundreds and hundreds of tools, right? So if you have like a GPT-4 model or like Llama 3 model, maybe you can support very long context lengths, right? But long context length has a lot of problems. One is that there's this lost in the middle problem where the accuracy goes down. It doesn't attend a lot to the things in the middle. And the second thing is that it's very expensive to run, right? As the prompt size grows, the amount of memory that you need to store the KV values increases, so that becomes expensive if you're running it locally. So one of the things that we worked on was this idea of tool RAG. So instead of like doing RAG, in traditional RAG, you're basically fetching the relevant pieces of information from like a knowledge base. Instead, for tools, we're basically fetching the right relevant tools, right? So for example, when I asked this tiny agent, create a calendar invitation with Lutfi and Sid at 2 p.m. tomorrow, I probably don't care about the map tool, right? So the LLM doesn't need to have the map tool definition in its prompt. It doesn't need to have like things related to like summarizing a PDF in its tool, right? In its prompt. So we thought of this approach of like fetching relevant tools dependent on the query. So what do? Like if you have like hundreds and hundreds of tools, which is the case with Apple, there's many different ways of operating the Mac. What do? So the first thing we can do is basically take the tool description and embed that tool description within like an embedding model, right? That's the first thing we can do. So let's say I basically look at this tool, find email address of a particular person, right? Find email address of Lutfi. And I just look at the tool's, a string, right? What's the function definition? Returns the email address for the given name. And let's say I basically encode this with a BERT model. So I encode this, I get a vector similar to Word2Vec. I get this X point here. But then if I actually look at the user's query, right? The user query is something like, what is Anna's email address? And I use like a embedding, like BERT model embedding or OpenAI's embedding, I get this point blue. As you can see, like, similar queries like find Bob's email address or write an email to John, all of them map to an area like this, but the embedding of the tool maps to a different location. Because the user query is different than what we write in the function description, right? So the key question here is, how can we create the right embedding for tools so that we can basically fetch the right tool for the user query that corresponds to using that tool? Okay. Or for example, another task is like this. If the user asks something like this, what is the weather like tomorrow at Berkeley? Let's say this is the user query. I need to use the weather tool. But if I use a naive embedding approach of, just embed this and then embed the function find weather, this is not going to be similar to this. So if I perform like a vector comparison, I won't be able to fetch this tool. I might as well actually fetch the wrong set of tools. Is the problem description clear here, what we're trying to do?
Yeah, Amir, so it is clear, but you're saying that, the text embedding is not sufficient in this case, right?
Exactly, for the tool description. Because in the code, we have a lot of we have input is this, output is this, right? So if I just take the tool, function description, it doesn't embed to the right space. And in code, you can see a lot of utility functions that don't have actually any, I can have like a utility function, which I need to use, but its description may have nothing to do with user's query. But I want to have access to that. So just basically using this like word-to-vec type approach or like an embedding approach that we use for RAG won't work immediately for function call. So what do we do? So what we can do is two things. So if you have very small number of tools, maybe you don't need to worry about this. If you have like 4 or 5 tools, just put that in your prompt and your LLM will hopefully figure that out. But if you have like very large number of tools, let's say greater than 100, then you do need to do this kind of like brings a subset of them. So you need to perform this RAG. So what we need is basically what we call a tool-to-vec approach. So you need to get your tool and provide a vector representation of that tool. So you may have already a domain-specific data set that includes different ways that this tool is used. So you have the user query and how many and which tools are used for that particular user. And if you have that kind of a domain-specific data set, then you can go and do something much better than simply embedding the function description. You can basically train a model, a very simple model, to perform a RAG operation for tools. So specifically, if you think about this problem, I don't know how many people are familiar with this retrieve and re-rank code. It's used in recommendation systems, right? So today, when you look at like Facebook or you look at Google, how they show you ads is there's millions of ads and there's billions of people, right? So there's no model can, look at all of the interactions and come up with the right ad, suggestion, right? So the way that this works is first they perform a very lightweight filtering of the relevant ads to the relevant people. So for example, for us, they look at our friends and what are they interested, or the city that you're in, and some other labels like that. And then they perform a more accurate, like an ad recommendation. It's kind of similar here. So what we're proposing is in this tool RAG approach is first you can get all of that thousands of tools that you have and perform a very fast retrieval method. So for example, if I'm asking about weather, I probably don't care about like a PDF analyzer, right? So I can very quickly use the approach that I showed you to remove, let's say 80% of, or prune out 80% of the irrelevant tools. And then if I have a data set that I can use to fine tune the model, I can create like a small DBERT model or a BERT model that can perform the second stage of fine-tuned filtering to give me the right set of tools. Is this framework here clear? What we're trying to do here? So basically,
is the first stage still based on like a word-to-vec embedding thing?
That's right. That's right.
I see. Okay.
But then you prune very coarsely here in the first stage. So in the first stage, you prone very, very coarsely. In the second stage, you basically, if you have enough, if you have like a data set of like user query and the corresponding tools, then you can basically perform the fine-grained pruning. So for example, here, when the user asks what is the better today, let's say you have multiple tools. The first stage only returns the better tool and let's say the map tool. And then the second stage, which is the more accurate stage, looks at this and returns the better tool as the output. Okay. So let me skip this MLC part. So this is basically the tool RAG method. So we ask the question, what is the better today? So first stage is this tool to back embedding. You basically have like a BERT model or like, text embedding from OpenAI that embeds the different tools. And then you look at the embedding vector for this user query and the results returned from this initial filtering. It, let's say, returns a bunch of tools. And then you fine tune a DBERT model that its task is to tell you which set of tools is the right tool to use. For example, here it returns the better tool. Right. In terms of results, so there is a tool bench data set that includes different difficulty levels. So level 1 is simpler. Level 2 includes more complex user queries, and level 3, the hardest task. We compared our approach with their original retriever model, which gets a model, which trains a model on this tool bench data set and tests, and as well as our tool RAG approach. So you can see that across all of these 3 different difficulties, we can get significantly better results with a very simple approach of tool RAG. I expect this to be, a lot more optimizations being done on top of this, because if you have like millions of tools, like, in the case of like SAP or Salesforce, you're dealing with, hundreds of thousands of possible tools that you can use. So there's more room here. All right, so in conclusion, basically, agentic applications, there's a lot of really interesting systems problems here. A lot of people are interested in deploying these things locally. So form factor matters, the model size matters. Like if you have a robot, like in 10 years, we're gonna have robots that will be going around the world, right? And those robots won't have cloud connection all the time. So they will need to be able to process the vision, process the user queries, make the right function calls locally, right? So we need to figure out a way to perform this kind of agentic applications with smaller form factors to enable that, to support that kind of a use case. I presented LLM compiler, which basically the main idea was to break the tasks into smaller modules. Another similar work is the DSPy work from Stanford, uses a different approach. It's more of like a framework, like a LangChain type framework that tries to approach the problem from a similar angle, which is more modular development. And I showed you a couple example workflows, like the Siri application that's deployed locally, and how it can be extended to larger set of tools with tool RAG. Right, that was it for this presentation. Thank you.
Right, we have like 5 minutes for questions. So
I have a question. Do you think there are any cases where actually doing things sequentially would use better results? Like because it gains some context about what it's searching on, and it's actually now like more knowledgeable about the thing when it's processing the next query.
Yeah, it is possible. So for example, yeah, I guess like, if like one of the queries says this company doesn't even exist, or like I have to think about like a use case, but let's say you make an API call and it says this API call is deprecated, then you don't need to perform any of the other API calls, for example. Right. So let's say, I'm making an API call to a database, and I'm using an outdated method, and I'm doing 5-6 of those kind of API calls. As soon as I see one of them gives me an error, there's no reason for me to call the other 4. But in this approach, I end up calling all 5 at the same time, and then returning like 5 error messages, and then it will be like, oh, okay, I need to use another API potentially. Although you can, of course, put some support for that in this framework too. You end up doing more work. So one of the things to consider is that you are now with this LLM compiler approach or the DSPy approach, you end up creating a plan, which you don't necessarily need to create this plan, right? So if I only needed to use one tool, let's say the extreme case is that I only needed to use one tool, in this approach it will be a little bit slower because you're creating a plan, then you're creating a DAG out of one plan and then executing it. But because of what we're seeing with this O1 model from OpenAI, it does seem like performing a little bit more operations and thinking during inference time is actually going to help you get better results. Good question.
So Amir, maybe as like a follow-up question to the IR part. So I mean, throughout your talk, I was thinking, you know, what is the IR? Because you wrote here search and then math, and then but you showed a way to figure out basically canonicalizing those tools as an IR. Like how flexible is that part, or how finicky is it? Like it feels like it you have like a nice general approach to it, but like does it work all the time? Have you tried to quantify how well it works? The refiner seems to be specific to the number of tools that you have. Are there limitations there? That part is quite interesting, I think.
Yeah, that's a great question. So in terms of the IR is pretty flexible, right? So you can basically, you know, write down different forms of creating this intermediate representation. One thing that we're working on, which we haven't figured out yet, was when we're writing code today, we have this x86 architecture, right? So we have this ISO for x86, right? And everything gets translated into those, you know, operations, right? When I'm opening an Excel, of course, I'm not writing x86. I'm writing code, let's say in like, you know, C#, and then there's a compiler that takes that and finally translates it into a set of x86 instruction sets. One of the questions that we were asking was, is there such an ISA exist for LLM agentic applications? If it exists, the great thing about that is that I can have very, very tight control over and tests around making sure that the execution is correct. So for example, like we tried this and it's hard to generalize this, but like a lot of agentic applications are like question answering, calling an API, calling another agent, right? Summarization, right? So if we have like a definition of, okay, there is a summarization, there's a question answering. If it's like a question answering, I can have another LLM and go and verify, is this the right answer, right? I can have some form of like tests around that. In the current approach we have, it's more open-ended because, you know, we basically provide the function definition, and the LLM planner's job is to create a consistent plan that follows this, you know, Pythonic approach, right? There's tasks, there's dependencies, and so forth. It's a little bit more flexible, but it doesn't, in terms of where it fails, it doesn't work with when you have very, very large number of steps that you need to take. It does support replanning, but it doesn't support very large number of steps, although we're addressing that in the second version of this. The tool refiner, Mohammed, what was your question about the tool refiner?
Like does it only support a specific number of tools? Like if you go to slide 49, it seems that you kind of have to train it on a specific number of tools available to you. Like, is there a general way of using this?
Yeah, that's a great question. This is following the standard retrieve and re-rank approach. So if you have a data set already available, which is like, given this user query, use these tools, given this user query, use these other tools, then you can use that standard approach. If you don't have that, then you have to use that, you know, word-to-vec type approach, which is like, look at the function description. Or one other thing you can do is you can use another LLM to create a better description for that tool and embed that one. Because usually if you look at like the function calls, you know, unless the code is very well documented, there doesn't exist enough of an explanation of what every function does, right? So you can have another LLM produce like a natural language explanation of what does this tool do, and then embed that one. But that approach doesn't work well because a lot of tools that you need to use are utility tools that need to be used for multiple different applications, right? Multiple different queries.
Yeah, I see. Any more questions from folks or from Ithaca? 1 minute. Maybe I have one more on the verifier.
Mhm.
So again, the verifier has to be somewhat general. So you did mention just, making sure there are no loops. So
Right.
that makes sense. But do you also have like tool-specific verifiers that you can put in there? Like you mentioned again, the example of well-formatted email address. But then for other tools, I imagine every tool will need some kind of verifier as well to its input.
Exactly. Yeah. So for every function call, you can have a specific verifier and, put some form of like, what happens if there is an error correction needed? If there's something happen, you can incorporate an error correction there. So for example, if you call an outdated API, or if you call an API and that API is for some reason throttled, right? You can go and, call an API, right? An alternative API. If the output is not well formatted, for some reason, like, if it's like question answering, you can have another model that looks at this question answer and makes sure that the answer is correct. If it's not, maybe dispatches it to another LLM to perform that kind of a task. So you can define a verifier for the plan itself, and you can define a verifier for every individual function call that you have.
Yeah, that makes sense. Yeah, very cool. Okay, if there are no more questions, I'd like to thank Amir again for coming. This was super interesting. So thank you.